Okay, thank you for coming to this talk. I should start off with a little background, but most of what I have to say is going to be sort of really hands-on, so you can see some of the stuff actually being implemented. So at Corning, our user base of JMP is growing, and not surprisingly, if it's been a while, if you're a very seasoned person in JMP, there was a painful learning curve associated with that. So we're developing courses to basically bring people up to a basic competency. The first course is actually a non-statistical course because we recognize if I have a problem that I need to use JMP to solve and I'm not a seasoned JMP user, now I have two problems. One is that I don't know how to use JMP. So this is just a portion of that course. I'll start right off. So this is broken into really sort of three sections from different parts of what that course might look like. Probably the last won't be included, but so basic point and click kinds of customizations you could make to annotate graphs and better highlight what your message is. And then some really simple JMP scripting customizations that I think everyone can do. If you have any familiarity with adding formulas to columns, for instance, and by the time they get this, they will, then this should be fairly straightforward. And the last thing is I talk about a completely JSL application where meant for as a teaching aid. Let me get started. Okay, this is random yield data. Random because I generated it. And so essentially, the scenario is you're asked to sort of nail down, as often can happen when we're trying to improve a process, we implement lots of different things that we think will improve the process, and then we get something that looks like this, and you want to know, what was it really that really did put the ball across the line? So in this sense, I'll want to narrow down something in time. So, and by the way, I put in sort of steps in here. I'll make this journal available on the website so everybody can, if you're interested, all the scripts and everything will be in it as well as a paper. So first thing, I like to set the point transparency. When points are solid, they tend to hide points that are behind them. The most recent points, the topmost points, hide whatever's behind them. And hopefully I get a good view up there. It looks great on my PC, but all right. And what you should be able to see is there's a darkness right here, and it gets lighter as you go out to the extremes and going across. So then we can, again, I want to narrow down the time frame. So I've colored the data by month going across now. And I can see, well, January, February, it looks like April. Something happened. Seems to kick in then. And I'm going to take advantage of the fact that a date is really, I can split that apart in this label row nesting, if you haven't seen that before. It has a month, a day, and a year, so I'm going to split those things apart, and I'll put a tick mark on here, say once every week, or one every 2 weeks, I should say. Okay. So now it's split out by year and month and day, so it's kind of a nice way to look at it. Then I'll add a smoother to it, which can be a challenge sometimes with when date is the predictor, I've noticed. But really, we just pretty much crank it up and we can see. So the general tendency going through these is there was a shift, and yeah, it appears it was sometime in April. So I might want to narrow it down a little bit more. In this particular example, what I will do is I'll use recursive partitioning. I'll use yield. There are lots of ways to do this, by the way. This is just one. Yield is my response, and date is my predictor. And the important thing here is to keep ordinal restricts order. So I get this, and it points looks like a mess, but because, as you recall, they're all colored by month right now, so it just sort of randomly puts those all over. I don't know that there's any reason to where they go, but if I just do one split, it looks like April 11th. It just pops right out. And so conveniently, especially if I didn't use validation, which I didn't this time, I can select all those points down below. So, by the way, this would say that before April 11th, the mean was about 96%, and afterwards it was about 98%. So it looks like something right around the 11th or 12th. And what I'm going to do is name that group of data as, we'll say, pre-shift. Right. In the data table. So now I have a new column in the data table that is phase. So going back to my previous chart, I'll remove the old month and I'll redo it by phase. And it did a pretty good job. At least visually to me, it did a pretty good job. Again, really all the goal would be here would be to, I want to nail down an approximate time period when it seems like we got the biggest bang for our buck. So I'll end this up with putting a little line in here on April 11th. I'll make it green and dashed line. Okay, so that's really that for that. So you can do quite a bit in JMP, as you probably already know. If you're very experienced in it, then that was probably a lot of review to you. But if you're not, then hopefully you picked up a couple things in there that I could reproduce that. Some folks deal with a lot of data that is in the form of, for instance, Likert scales, and depending how it's entered, it can be helpful or not. As it stands, if it isn't entered as integer values or minus the plus values, then it sorts it in alphabetical order by default. So to dress up a plot like this, you really need to get those things in the right order. And for sake of time, I'm just going to do that like that. But I will show you what it looks like. Well, I didn't do it anyway. So basically, I bring up, this shows me all the values that are in that column, and I want to sort them in the order that makes sense to me. So strongly disagree, and then disagree, neither, agree, and strongly agree. Okay. And I'll make that histogram again. So now everything's in the right order. So again, if you haven't seen that before, there are a couple of things that when you're first learning, they're very frustrating, but usually the capability's there. It's just, can I figure out how to do it? One thing I would point out at this, I should have said before, it's really important to save these customizations as you make them, because I might want to apply this same plot as I get more data in the future. So lots of ways to do that. One of my favorite ways is to hit the little drop down and script and save script to data table. And now I have that new script in there. And the other thing is for folks who program in VBA for Office or any of those sorts of things, it's very much like VBA in that you get to see sort of the code. It might not be exactly the way you want it as it is stored, but it's a starting point to customize. Let's see. Railroading was covered last time. you get a lot of bang for the buck by spending a little bit of time in the data table setting properties, which is one of the things we'd like to encourage our students to do as they go through this course in Corning. So for instance, right now, if this is, by the way, JMP sample data, so you're free to try this on your own. It's called Diameter, and it's basically data from a company that manufactures catheters, blood transfusion tubes, and other medical application tubing. And they didn't give specification limits, but I'm going to impose some on it. You can see when I put specification limits or set any of the column properties, I usually get this little asterisk, and I can say, oh, it's got spec limits set. So what I did is in the description, they said they were going for a nominal target of 4.4, and I said, well, let's just assume for sake of argument that it's plus or minus 0.4. So I want to show as graph reference lines, make sure that's selected. So then when I do things like that distribution again, I get a nice count over here, actual count of how many were outside those limits. So again, if you're not familiar with that, that's a big time saver over counting things or setting up column formulas. All right, so that's most of the non-JSL. I'm going to go through some pretty simple examples of how you can annotate graphs with JMP scripting. Yeah, and this is a graph from JMP sample data. Happens to be nice description in here. This is data from a physics class where they're essentially measuring the period of a pendulum, how long it takes to go, say, for one complete cycle as a function of its length. For those of us who have had the physics, once upon a time at least we knew this equation, and I had to look it up, but I do know it now. So we look at this and say, well, that's a nice smooth curve, you know. I think maybe I'll fit a quadratic to it. And well, I won't go through all the different types of linear models you can fit to this. I can assure you none of them do a very good job without some sort of transformation. And there's a reason, of course. So what I'm going to do is use a little JSL to add the function that I know fits this data. Or at least should. So I right-click anywhere in the graph and say Customize. And so right now I have things in here like grid lines, reference lines, and markers. I'm going to add a script in here. This is this plus sign. And this can be a little intimidating in first if you don't know JSL, and even if you do, it's a different part. The nice thing is that there's some drop downs here that give you some little code snippets that you can just go in and modify, which is beautiful. That's the thing of beauty. Need more stuff like that. But I'll set the pen color and say the pen size, and of course I need to put that function in. So pen color, I'll make, say, green. And lost my mouse here. Pen size, I'll say 3. So that's just it's going to be a green line. It's going to be, I think, 3 pixels wide, or I don't know what the 3 actually stands for, but it's bigger than 2. That I do know. And the function happens to be 2 pi times the square root of the length of the pendulum over gravity. I'd love to stand here and say I knew that from college, but it had been a long time. Now, before I leave this, so what this is saying, the y function part, is so here's this y function, and that's the function. And it's going to take, I'm going to feed x values into it. Those x values are coming from whatever the x-axis is. So if I expand the x-axis, then there's more values that'll be plotted on here. It's the beauty of first principles models, I suppose. And you can see it does a pretty good job. Okay. So going back to the yield data, if I were to have, instead of plotting that over time, again, it looked like this. If I just did a histogram of that as my first look and say, well, I went into, I'll do it quick. There's yield. And I want to fit a distribution to it. I can say continuous fit all. All right. Stir gently, and what it says is normal 2 mixture is the best, and it's on there. It's actually on the other plot too. And so I've had questions in the past, so like normal 2 mixture, can you explain that to me? What is that really doing? So one nice way of showing this, if that ever happens to you, is to show the individual distributions on this plot. So what it says is I have 2 distributions. One of them has a mean of 95.9 and with a standard deviation of 0.89, and one has a mean of 98.04 with a standard deviation of 0.908. And this is the proportion of the 2 distributions. So I'm going to go ahead and add those on. All right. And I'll set pen size. I'll do this for one, and then I'll show you the completed one. Fill color. There we go. And so again, I'll use green. So I would have to do this twice. Right? I have 2 distributions, and I want them different colors. And what I'm going to put here, I'll just read it out of this table. So the first one, you see right here is 0.2786 times the normal density of using x as a variable. And if you look at the nice thing about these is you can point at them. I don't know how well you can see that. And it'll give you the function arguments. That's a really nice thing, nice feature. So for this, it takes an x mean and a standard deviation. So the mean is 95.961, and the standard deviation is 0.8919. And again, I'm getting those out of this table right here. There's the first mean, and there's the first standard deviation, and the 0.2786 is the first proportion. So when I apply that, nothing happens. And the reason for that is this is sort of the order that things are plotted on this graph, that they're painted on the graph. So at first it does grid lines, then my little normal distribution, then reference lines, then the histogram, which covers everything up, and then on top of that histogram, this normal 2 mixture. So I can just click the up and down buttons to bring something forward right through here. So you can see there's the little piece of the low end of that distribution. I actually have it, the completed example. So there's both pieces. So I can take these 2 things and add them together, and it makes the red plot. So it's a nice way of showing how that works. And again, it would be really difficult to plot this in another package. You could do it, but okay. One of the things I use a lot is I like a graphical representation of gauge R&R, measurement systems analysis. And so This is one way that we show it. I'll show you the code behind this, but essentially you go in and you say, here's the upper spec, the lower spec, and here's the R&R standard deviation. And I apologize if you don't know those terms. I apologize. I don't have the time to explain them. But for my industry, I know them almost too well. And so I like to show the sort of gray zone around my specifications. So where I can't trust one measurement, I might have to remeasure anything that falls in those gray zones because it's within measurement error, it could be out of spec. So what does that look like? So this is a script that really, I'll need to proceduralize more, but again, it's just building a little at a time, probably on a day 2 course if people get into this at Corning. But really, I want something where I go in and I set these values and I get that plot, because we do a lot of gauge R&R. All right. So I'll try to quickly go through this because I'm running out of time. So this is something for anybody who works in with brittle material science, this might be near and dear to you as it is to me. So this is a Weibull, 2-parameter Weibull fit to some fictitious strength data. And one of the things you'll note is well, from our eyes, what you should know is this is a very poor distribution fit. From a brittle material scientist's eyes, they would say that actually the old school guys would use, and women would print out the Weibull plot and actually draw 2 lines on it. So wouldn't it be interesting to know what that PDF looked like? Well, I won't go through how I got it, but it was a spline regression where there's a knot right there where those 2 lines meet with some restrictions, and then not a spline regression, a nonlinear regression of a spline fit. And that's what it looks like. So basically I have a piece of one distribution, and then I take scissors and cut it off and put a piece of another distribution. It's pretty common in the literature that you see stuff like this, but I never see that plot in the literature. To put that on there, essentially, this is my Y function just like before, but I'm putting a little extra logic in there and saying basically if X is less than some value, use this Weibull density. Otherwise, which is a comma out there, use this Weibull density. Again, this is where some familiarity with doing worksheet or column formulas would be really helpful. So I'll show you a couple. I think I got time for a couple more quick examples. So another thing you could do is another nonlinear regression where I say, I think there's 2 Weibull distributions there, and I'm going to give it a mixing parameter, very similar to the normal 2 mixture that we did originally. So here's what that looks like. And in order to plot that, so I say it's some proportion times the first Weibull density plus 1 minus that times the second one, just like we did for other things previously. Something we've looked at a little bit, we didn't invent it, it's in the literature, is something called forced percentile censoring. Where this is where basically we say, so people are not really upset with us when things have a really high breaking strength, amazingly enough. It's the weak ones that they care about. Golly, we should probably do a better job fitting the low tail much better job, because I don't have an upper spec on what kind of strength glass would need to, if it's infinite, it would be the upper spec. But there's a lower spec. So there's a method where I can censor the data and recode it a little bit at that censored value. And I don't have time to go into it fully, but when I do that, see, it does a much better job. This is the lower tail percentiles, where all the action is, so I want it a good fit down there. And it looks like this. So it's basically we're thumbing our nose at the strong part of the distribution in order to do a good job fitting the lower tail. So we're still kicking that around, actually. And just real quickly, I can put all of those on one plot. There's no issue with doing that. It is a busy plot. I don't like busy plots, but it is possible to do. So this is something that I actually modified, something that was a jump sample file, sample script, and it took forever because the jump scripting model is something that it took me a while to get used to. I programmed in VBA and C and Java and Python, and it just was a little bit different for me. Just like anything that's sort of object-oriented, you need to learn the objects and what their properties and methods are. It's a little bit different than that. But still, it's not impossible, so you can actually make stuff. This is a lot of people, I've given this to a lot of folks at Corning, so that they can, they're like, what does the scale parameter do for the aim? I don't understand what that means. Or what's the shape parameter? I've heard people say that if it's between 3 and 4, it's approximately normal. I mean, do you have a picture of that? I'm like, well, as a matter of fact, I do. So you can do things like this, and again, this is in the journal I'm making available. So if you're interested, you already have it if you want it. Okay? Where to get more help? Actually, there are a couple really great books once you get towards the scripting side. I really enjoyed and learned a lot from the Jump into Jump Scripting. It's like a purple covered book. I don't get any commission for saying that, but I really found it helpful. And there's another, the JSL Companion Applications of Jump Scripting. In addition to the Have You Tried and the webcasts, and all of that's been really helpful. Okay, and I thank you very much. It's off. I'm supposed to remind you, if you have questions, you have to hold down your button. So either I did a fantastic job, or I underwhelmed you. That could be true. You find a lot more savvy jump users at the Jump conference, surprisingly enough. There's a talk. Yes.
So when you create a custom function in your graph,
Yep.
did it actually do a fit analysis to give you the R squared of the fit?
No. I'm providing an equation. Now, sometimes that equation is a built-in jump equation, like normal density, but in general, no, it's not doing anything like that. I'm providing all the information, and it's just showing it for me.
Okay.
Yes.
Okay, I had one question. You had 2 cases where you used a mixture of 2 Weibels, and you also had one where you truncated or censored out the right-hand part and just kept the tail because you wanted to predict what was happening in the tail of the distribution. Did you see any difference in inference? If you go to do inference and to predict, put confidence bounds on the prediction for the low end of the tail, does a mixture provide tighter confidence bounds because you're using all the data versus censoring because you you're getting rid of all that data in the upper
This is
end.
what we argue about. Well, because it's situational. If I were in a percentile sensor, for instance, what's the right value? What's the right percentile to sensor at? The 25th, the median, 75th? Should I, maybe it's not a percentile, maybe I should just have a value and do what at Corning we call proof testing. So I test up to a limit on things like optical fiber, and if it doesn't fail, it's at least that strong. Okay. But it's all censored. So I think the real acknowledgement is, what's my purpose of fitting a distribution to it anyway? If it is so that I can predict lower tail percentiles or some function of them like yield or CPK or something like that, then I want to put as much focus on that low tail as possible, and which means I don't just fit a 2-parameter Weibull if it doesn't fit well. But if they're competing techniques, and really I don't have a concise recommendation on which one to use. They both do well at times and comparable results.
That's all the time we have for this session. The next one, well, now we have a break, and the next one starts at 2:45. But thanks again, Casey, for a great talk.